Hello and welcome to another session in number theory. In this session, we are going to see how numbers are represented in different bases. We usually use base 10 for representing numbers. That means whenever we see a number, usually it is represented in base 10 even though it is not explicitly mentioned. So, what is the meaning of representing a number in base 10? We will see it using a small example. So whenever we write a number in this form, suppose that we are writing the number 1, 2, 4, this basically means that 1 has a position value of 1 into 10 raised to 2, 2 has a position value of 2 into 10 raised to 1, and 4 has a position value of 4 into 10 raised to 0, which is essentially 1. Therefore, the total value of this number is actually 1 into 10 square plus 2 into 10 raised to 1 plus 4 into 10 raised to 0. That means that every integer will be having a value of that integer into a power of 10. Therefore, this representation, we call this as the decimal representation or base 10 representation. Base 10 representation in which every integer will be having a place value of that number into 10 raised to a power. So it is not actually necessary to use base 10 all the times. For example, in computer science, the base 2 representation is very commonly used. So in base 2 representation, 2 is the base, whereas in base 10 representation, 10 is the base. Recall that in base 10 representation, we have 10 digits to represent a number, which are 0, 1, 2, etc. 9. These are the digits used to represent a number in base 10. Whereas in base 2, we will be having only 2 digits to represent a number, and these two numbers are 0 and 1. Therefore, whenever we have a base B representation, this means that we require B digits starting from 0 to represent a number in that system. And every integer, every number that we will be using in an expression of a number will be having place value that number into the power of d and some power of d depending upon where that integer is exactly appearing. So in this session, precisely what we are going to do is we are going to see how to convert between different bases and how to understand what exactly the bases are and all these things. It is possible to represent a natural number in any natural number base. As we already mentioned, we can represent a number in base 2. There is no point in representing a number in base 1 because in base 1 there will be just one number to represent any other number, which is 0 itself. And since that's pointless, we will be using natural numbers from 2, 3, etc. as bases. So what exactly is meant by a base B representation? We are going to state the definition of what we meant by a base B representation. So definition is the following. Base B representation where B is a natural number greater than or equal to 2. The following expression n equal to ak into b raised to k plus ak minus 1 into b raised to k minus 1 plus etc. plus a1 into b raised to 1 plus a naught into b0 is known as the base b representation of the natural number n. Therefore, this is basically an expression of the form ak into b raised to k plus ak minus 1 into b raised to k minus 1 plus etc. and ending with a1 into b raised to 1 plus a naught into b naught. Usually, when we use the base 10, we say that this a naught is coming in 1's place, a1 is coming in 10's place, etc. So, if we use this as the definition of base B representation, then we have 1, 2, 4 we have already seen that 1 to 4 can be represented in this way. So now, how do you find the base pair representation of a natural number? For example, suppose that 124, that is actually a number given in the base 10. How can we convert the base 10 representation of 124 into, uh, for example, say base 8? So the question is the following: convert 124 in base 10 to base 8. So what do we actually need is we need to represent 1 to 4 using digits, that is present this number using digits 0 to 7, because in base 8 we can use digits 0 to 7 only, and we cannot use 8, 9, etc. So, how do we perform this conversion? That is the question. For converting 1 to 4 into base 8, just remember that how did we wrote the expression for 1 to 4 in base 10? So, we took the largest 10th power that can be accommodated in 1 to 4, which is 10 square. Then we took the largest, uh, the least second largest 10 power that can be accommodated in the remaining thing. Just say that if you are taking 1 into 10 square, and that's 100, and if you remove that 1 into 10 square, 100, then 24 is remaining. Now find the largest 10 power that can be accommodated in 24. After that, we get it to be 2 into 10 raised to 10 raised to 1. Just remove that 2 into 10 raised to 1, which is 20, and therefore 4 is remaining. Therefore, the largest 10 power that can be accommodated in 4 is nothing but 10 raised to 0, and therefore the remaining is 4 into 10 raised to 0. That is what the procedure that we adopted for finding the decimal representation of 1 to 4, or for finding the place values of digits in 1 to 4. Exactly the same step we have to follow here. Therefore, in 1 to 4, what is the largest power of 8 that can divide 1 to 4? You know that 8 raised to 0 is 1, that can be definitely accommodated, that is less than or equal to 1 to 4. This is less than or equal to 1 to 4. Now, 8 square, before that, sorry, 8 raised to 1 is 8, that also we have to choose. 8 raised to 1 equal to 8, that is less than or equal to 124. Therefore, 8 also can be accommodated. 8 square, that is equal to 64, that is also less than or equal to 1 to 4. And if you take 8 cube, that is going to be more than 480. Therefore, that cannot be accommodated in 1 to 4. Therefore, we can see that the largest power of 8 that can be that is that will divide 1 to 4 is 8 square. So we first of all write 1 to 4 equal to 8 square into how much will be included in 1 to 4. We are basically going to use division theorem. We are going to use division theorem here. So 8 square into 1, that is 64, and after that 60 is remaining. Now we are going to take out, so 64 is already included, therefore 124 minus 64, that's already taken, that's remaining is 60, that's already here, the remainder is already here, we need not look anywhere else. So 60 is the remainder. Now we write 60 equal to 8 raised to 1 into something plus something. What is this? 8 raised to 1 into, we can have 7 here because it is 56. So 56, and what is remaining is 4. Now the remainder is 4. Now we write the remainder 4 equal to, remainder 4 equal to 8 raised to 0 into 4 plus 0. Now there is nothing more remaining. Therefore, the digits we are getting is, largest one we are getting as 8 square into 1. So 1. Next one we are getting is 7. 8 raised to 1 into 7. So next is 7. And after that, we are getting it to be equal to 8 raised to 0 into 4. Therefore, the number 124 becomes the representation 174 in base 10 equal to 124 to the base. So we are basically using division theorem for finding out the digits in the representation to the base 8. Now, to convert the number 174 to the base 8 back to base 10, we can exactly, the same procedure can be followed. That means 174 is nothing but it's equal to 1 into the largest power. See, we have to count from the last. We have to count from the end. So this is 8 raised to 0, 4 is at 8 raised to 0, 7 is at 8 raised to 1 is at 8 raised to 2, which is 8 square. So 1 into 8 square plus 7 into 8 1 plus 4 into 8 raised to 0. Therefore, this becomes 64 plus 56 plus 4, which is essentially equal to 124, and this is to base 10. So converting back to base 10, we have to follow exactly the same procedure. So just remember, recall that a base pair representation is nothing but it's an expression of the form n equal to ak into bk plus ak minus 1 bk plus 1 plus etc. Where one important thing we forgot to actually mention is ai are from 0 etc. up to b minus 1. These are the digits ai we can use. This is known as base b representation of a number. Now we will see one more example to familiarize ourselves with base p representation. So the question is the following: convert 135 base 10 to base 2. We will follow exactly the same procedure. So 135 equal to, what is the maximum power of 2 that can be accommodated here? The maximum power of 2 is going to be 2 to the power, the largest power that can be accommodated is 2 to the power 7, which is 128. So 2 to the power 7 into 128, remaining is 7. Now the remainder 7, and now we cannot actually stop with we know that largest power of 2 that is contained in 7 is 2 raised to 2, which is 4, but we cannot just write like that. Instead of that, we have to take all powers of 2. Even though no power can be accommodated, we have to take 0 as the contribution from that power of 2. That means 2 raised to 6 we have to consider. 2 raised to 6 cannot be contained in this. So there is actually a difference from what we previously saw. Here, 2 to the power 6 cannot be actually accommodated here. The condition that we have to start from the largest power of 2 that can be contained in 135, or in general the largest power of b that can be contained in the number n, is applicable only in the first step. Afterwards, we have to consider all powers of b. So 2 raised to 6 into 0, 2 raised to 6 into 0 plus 7. Now again 7 is the remainder and 0 is the contribution from here. 2 raised to 5 into 0 plus 7. 7 equal to 2 raised to 4 into 0 plus 7. 7 equal to, we have to come down to all the powers of 2. 2 raised to 3 into 7 plus 0 plus 7, and 7 equal to, now we are in a better situation. 2 square into 1 plus 3. Now going down further, 3 equal to 2 into 2 raised to 1 into 1 plus 1, and one more step, that is 1 equal to 2 raised to 0 into 1 plus 0. Therefore, the numbers that we got, the remainders we got are, initially we got not remainder, the quotients we got are, initially we got 1, we have 0, we have 0, we have 0, we have 0, we have 1, 1, and finally 1. So if you write all these things together, then 135 to the base 10 will become, in base 2, 1, 0, starting from the top. 1, 0, 0, again 0, 1, 2, 3, 4, 4 zeros, then 1, 1, 2, base 2. This is the base 2 representation of 1, 3, 5. Another important point is in the case of 8, we have already seen that a base 8 representation is also known as octal representation, and base 16 representation is known as a hexadecimal representation. And in base 16, the digits are 0, 1, etc. up to 9. We need 16 digits. So instead of, you cannot use 9, 10, 11, etc. because that will be confusing whether we mean 10 itself or we mean 1, 0. Therefore, instead of that, instead of 10, we have A, then B, C, D, E. 10, 11, 12, 13, 14, 15, and F. These are the hexadecimal digits that we are using for representing a base 16 integer. To find the base p representation of a natural number n, we can in fact use division theorem, and which is easier than finding out the largest power of p in the natural number n and then taking dividing that n using largest power, then again dividing using the next largest power, etc. The procedure can be described as follows. Now, the question is to find the base p expansion, base p representation of natural number n using division theorem. Suppose the natural number is n. We have to find base p representation of natural number n where p is greater than or equal to 2. Now, recall that by division theorem, we have n equal to, we can divide n into using b in this following way: q naught b plus r naught, where r naught satisfies 0 less than or equal to r naught less than b. Now, just remember one more thing, that we are dividing n using b and q naught is the quotient. Therefore, q naught is going to be less than n, or n is going to be greater than q naught. This is strict. Now, we can further divide this q naught equal to q1b, again using b, plus r1, where r1 still satisfies 0 less than or equal to r1 less than b. Now, we have this q not greater than q1. Next is q1 equal to, following the same procedure, q1 is equal to some q2b plus r2, again q1 going to be strictly greater than q2. If you continue like this, since q0 n, q0, q1, q2, etc. are strictly decreasing and are all positive, we will finally get q k minus 2 equal to q k minus 1 into b plus r k minus 1, and in the last step, definitely this q0, q1, q2, etc. it's decreasing, therefore it should become equal to 0. It should not become, not necessarily going to become equal to 0, it must become less than b. Therefore, finally, in the last step, we will be having q k minus 1 equal to, it cannot, it became less than b. When it becomes less than b, we stop. 0 into b plus what will be remaining, equal to q k minus 1, where 0 less than or equal to q k minus 1 less than b. We stop at this step. Now we are going to perform some accurate substitution, in the sense that n we have equal to q naught b plus r naught. So n equal to q naught b plus r naught, but q naught is nothing but q1 b plus r1. So this is equal to, for q naught we are substituting q1 b plus R1 into B plus R naught, which on expansion we get Q1B square plus R1B plus R naught. If we keep on substituting, now we substitute for Q1, after that we substitute for Q2, etc. Finally, we will be getting the last, after performing all kinds of substitution, we get Qk minus 1 Bk plus Rk minus 1 Bk minus 1 plus etc. plus R1b plus R naught. Therefore, the base B representation Qk minus 1, we have already made sure that that is less than B. Therefore, the base B representation is Qk minus 1 Bk plus Rk minus 1 Bk minus 1 plus etc. R1b plus R naught. Just observe that what are this R naught, R1, R2, etc. R naught is the first remainder, R1 is second remainder, etc. Rk minus 1 is the second last remainder, and Qk minus 1 is the last remainder. Therefore, we are continuously using division theorem and performing divisions, and we are taking only the remainders for representing the natural number n in base B. So we are using only division theorem for performing the representation of n in base D. Let us try this procedure for one of the examples that we had previously, and that example is that of 124. Okay, 124, we want to convert that into base 8. Okay, the number we have is 124. So the question is, find the base 8 representation of 124. So our n is 124 and b is 8. Now we apply division theorem. So 124 equal to, we have to find how many 8s are there, and 15 into 8 is 120. So 15 into 8 plus 4. So we have R naught here. Now this is our Q naught. Now 15 is equal to, how many 8s are there? 15 is equal to 1 into 8 plus 7. This is our R1. This is our Q1. Now, what about Q1? Q1 is 1. 1 equal to how many 8s are there? 0 into 8 plus, now what's remaining? 1 is remaining. This is our R2. So, the representation of n, we have to take this way, starting from the bottom. So, n equal to 1, 7, 4 to the base 8. So let us see if it matches with our previous calculation. So 1 to 4 we found to be 174 exactly here. So calculation seems to be justified. We will see one more example. The question is following. X plus 2076. This is in base 10, in base 16. So we are supposed to find the hexadecimal representation of 2076. Again, going to use the same division theorem technique. 2076. Now we have to divide using 16. So let me use the calculator. So 2076, 16. Therefore, it is 129 into 16. So what I did is just I divided 2076 by 129 using the calculator, and then took the integer part, because we know that the number of 16s that's in 2076 can be found by dividing 2076 by 16 using decimal division, and just remove the fraction part. Plus, now what is remaining? 129 into 16 is 2064. So remaining is 12. Now let us divide 1 to 9. This is our R naught. This is our Q naught. 1 to 9 using 16, and we will get to that. We will get it to be 8. 8 into 16, that's 1 to 8 plus 1. Now this is our R1. This is our Q1. Now 8 is equal to how many 16s are there? 0. Therefore 0 into 16 plus 8. This is 2. So again we are going to take the remainders in the reverse order from the bottom to top. So we will get 2076 equal to base 10 is equal to 8 1. Yeah, there is one important thing to remember that 12 we cannot write as 8112 because it will be read as 8112 in base 16. That is not correct. So instead of 12 we use a symbol. Remember that the symbols that we use for 10 are 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. So 8 1 C to the base 16. This is the conversion. Now, if you want to check whether this is correct or not, the technique is to reverse steps in the sense that find the decimal representation of 81C. So, how will you find the decimal representation of 81C? Next question, probably we can take it to be that. Question is this: find the base 10 representation of 81C, which is to base 16. So to find it, write 81C to base 16. Remember that every integer, every digit here represents a power of 16. So starting from the rightmost, C into 16 0 plus 1 into 16 1 plus 8 into 16 square. But C in decimal digit, this is A, B, C, 9, 10. Oh, what was it previously we had? A, B, C, that's correct. So we have C equal to not 9, 10, 11, 10, 11, 12. Therefore, this is 12 into 16 is 0 plus 1 into 16 1 plus 8 into 16 square. On computation, this is 12 plus 16 plus 8 into 16 square. I'm just using calculator once again. This is 2048. 2048. Therefore, 2048, 16, that is 2064, that is 2076 total to the base 10. So the previously we converted 2076 and we got 81C. Now we are converting it back to get 2076. Therefore, this justifies that whatever we have, and this actually verifies that whatever computation we have performed is actually correct. Now we will see a slightly different question. Question is the following: if 54 to base B is equal to 64, find value of B. So in such situation, what we have to do is we have to take the expansion decimal. We have to try to convert it into, because 64 there is no base given, therefore we can assume that 64 is to base 10. So we expand 54 to the base B and convert it to base 10. So 54 to the base B is nothing but 4 into b raised to 0 plus 5 into b raised to 1. Therefore, this is 4 plus 5b, and it is given to be 64. 4 plus 5b equal to 64. Therefore, 5b is 60, or b is equal to 12. Therefore, the base here is 12. One more question of the same type. Find b if 1001 to the base b is equal to 126. Again, the same kind of technique. 1001 to the base b is equal to, we are starting from the end, 1 into b0 plus 0 into b to the power 1 plus 0 into b square plus 1 into b cube. And this is nothing but 1 into b0, that is 1 plus 0, 0, 1 into b cube is b cube itself. Therefore, if we equate this 1 plus b cube and 126, we will get b cube is equal to 126 minus 1 equal to 125, so that b is equal to 5. So the base is 5. Now we have a different question. The question is to arrange a few numbers given in another base in some order, ascending or descending. Arrange. The numbers are the following: 1011, 110, 11011, 10110, 101010 in increasing order of magnitude. So to solve this problem, we have to just recall what we actually do in the case of arranging numbers in the decimal form. See, in decimal form, what we do is that since the leftmost number is non-zero, how do we compare the numbers? The number with maximum number of digits is the largest. So we can take that number to be the largest. So we have to check the number of digits first, and we need some extra comparison only when two numbers have the same number of digits in that. Here we have binary digits or bits. So what is the number with the least number of digits? 110. Therefore, that is probably the least number. What is the number with, so 3 digits are there. What are the numbers with 4 digits? 1011, etc. What are the numbers with 5 digits? 10, numbers with 5 digits in the given order: 110, 11 and 10110. These are 5-digit numbers, and 6-digit number 101010. Obviously, this is the largest one because 6 digits only for one number, and this is 3 digits only. Therefore, this is smallest. 4 digits next smaller. So now we need to compare these two. That's the only thing remaining. Now, how do we compare when we have two decimal numbers with same number of digits? So we need to start comparing from the leftmost position. So here the leftmost position is 1. Here also the leftmost position is 1. Next position is second leftmost is 1 here. Second leftmost is 0 here. Therefore, the largest number is going to be this one. Therefore, we need to arrange it in the form 110, 1011, 10110, 11011, and last number 101010. This is the increasing order of the given numbers. Just see that we don't have to convert it back to decimal expansion for finding out whether it is which one is larger, which one is smaller. We need to just observe or recall that what we exactly do in the case of decimal numbers, exactly the same procedure will work in the case of base b numbers also. The only thing we have to remember is that only thing we have to keep in our memory that a base p representation is it's nothing special, and base 10 representation is of course nothing special, and the same properties base 10 representations will be having will hold for all other base representations. And we stop our discussion on numbers and different bases with these problems, and probably we can try you can try some more problems, some more exercises, and make sure that you have properly understood the concepts of conversion and the techniques of conversion among different bases. Thank you.